Hello everybody. This is just a short little sort of supplementary tutorial on the fundamental theorem of calculus, and specifically on how to tackle some of the questions that tend to turn up about the fundamental theorem of calculus on exams and worksheets and the like. So I've got two examples here that I'll just quickly run through, and hopefully you might find it helpful. Okay, so the first one, as it happens, comes from the 2018 summer paper in this course. And it presents us with this function a, and a of x is defined to be the integral from 1 to x of t log t. And it's defined for x greater or equal to 1, which means that basically the upper limit of integration is to the right of the lower limit. And our question here is, what is the derivative of a at e? And so in order to answer a question like this, I guess we know that the fundamental theorem of calculus tells us exactly about derivatives of functions of this type. So it tells us that if we, and I guess the thing to sort of give your attention to with a question like this is how exactly the function a depends on its argument x. It's to the upper limit in an integral. So this is saying that a is the function that takes x, which would be a number at least equal to 1. And what it does with x is it takes the area enclosed between the vertical line, x equals 1, the vertical line through 1, of the region enclosed by the horizontal axis and the graph y equals t log t up as far as the right-hand endpoint of the picture, which is where x is. So whatever x is, a takes that area as far as x. So of course the value of a varies when x varies. What the fundamental theorem of calculus tells us is nothing about the values of a itself, but that the derivative of a at a particular x is just the value of this function, this integrand at x. So it will just be x log x. And this is true for x greater or equal to 1 in the domain of a. So the answer to the question then of what is the value of the derivative of a at e, well, it's just e log e. The log of e, of course, is the power to which you have to raise e to get e, so it's 1. So this is just e, since the log of e is 1. Okay, so the answer there is e. And the key point is we've got an area accumulation function, and we're asked about its derivative. So that's just a direct application of the fundamental theorem of calculus. And what the fundamental theorem of calculus says about this particular example is precisely this. It tells us exactly what the derivative of a is in terms of x. If you want to know that at a particular value, like e, you just sub in that particular value of x. Okay, so that's one sort of very typical example of a direct application of the fundamental theorem of calculus. Here's another one, a slightly more complicated example with a few parts. This one also is from an old paper in this subject. It's from the summer 2015 paper. And here we're given a function a, again, very similar. A is an area accumulation function for something. This particular a, what it measures is area accumulated under the cosine graph from 0 to some x. X is the argument of the function for different values of x. This function takes an area of a region with a different right-hand endpoint, and this time it's defined for x at least equal to 1. So there are 4 parts in the question. The first part asked us for a diagram that indicates the meaning of a of x, and maybe even if you're not asked for it, this is sort of a good habit to get into if you're thinking about these area accumulation functions, just to draw a picture that sort of captures what they're doing. So this particular a calculates the area of a region whose left-hand endpoint is at 0. Okay, the graph in question is the graph of the cosine function. So let's draw a bit of the vertical axis through 0. Let's say that 1 is here. The value of the cosine function at 0 is 1. So I'll draw this bit in another color. The cosine function decreases as x increases from 0. By the time we get to pi over 2, the cosine of pi over 2 is 0. So this is pi over 2. Then it goes negative, it goes down to minus 1, which it reaches when we get to pi. It reaches 0 again when we get to 3 pi over 2, and so on. So that's a bit of the graph. This is y equals cosine t. T is the variable that parameterizes the horizontal axis in this picture, and that's sort of how the picture goes. So our function a is defined for x at least equal to 1. 1 is somewhere here, less than pi over 2. So a potential value of x, for example, would be here. And what the function a of x does is it just takes the definite integral from 0 to x of the cosine function. So if we take account of all that area, counting area below the x-axis as negative, of course, but basically a of x is the shaded area with the part below the x-axis, below the t-axis, counted negatively. If you didn't say that, I would not hold it against you in an exam. So really, any kind of picture like that sort of just shows what the function a is doing. So what a does for a particular value of x is basically take account of that red area. Okay, so that's what a does. It's the area accumulation function for this graph, which is drawn in green. So any picture at all like that would explain what the function a is doing, and would certainly get full marks from me on an exam. Okay, second part of the question, show that a evaluated at pi over 2 is 1. So here we must consider carefully what we're asked to do. So we're looking for a value of a here. Okay, what's a of pi over 2? Well, to determine what a of pi over 2 actually refers to, we've got to put pi over 2 instead of x in the definition of a. We've got to sub in pi over 2 as the relevant value of x. And when we do that, we can say, well, a of pi over 2, okay, a of x in general is integral from 0 to x of cosine t. So a of pi over 2 is integral from 0 to pi over 2 of cosine t dt. So in order to determine the value there of a at pi over 2, we have to do the integration. We have to calculate this integral. That means we need to take an antiderivative of cosine of t, evaluate it at the two limits of integration, pi over 2 and 0, and subtract the value at 0 from the value at pi over 2. So an antiderivative for cosine t would be sine of t. If you don't remember that immediately, don't worry about it. We're going to talk a lot more about that in the coming weeks, about how we find antiderivatives for things. We've got to evaluate that at pi over 2 and at 0. And so the conclusion is that this should be sine of pi over 2 minus sine of 0. So sine of pi over 2 is the y-coordinate of the point that we reach by traveling the distance of pi over 2 around the unit circle in an anti-clockwise direction from 1, 0. That's 1. This is 1. Sine of 0 is the y-coordinate of the point 1, 0, which is 0. So the answer to that is 1 minus 0, which is 1. Of course, I care not so much about the answer as about what we need to do and how we understand what it is that we're asked to do. Okay, part 3 of this looks very like it. The difference between part 2 and part 3 and how they're written is only this little dash in part 3. But in part 3, we're not asked for a at pi over 2, but for a dash at pi over 2. Here, it's an application of the fundamental theorem of calculus, which tells us that in general, the value of the derivative of a at a point x is the height of the graph above or below the y-axis at that particular point x. So it's just cosine of x. A dash of x is cosine x. This is by a direct application of the fundamental theorem of calculus. The previous one is also by an application of the fundamental theorem of calculus, but more to the technique of calculating integrals here. This is exactly what the fundamental theorem of calculus says about this example, that the derivative of this function a is just at x is just cosine of x. Okay, so a dash of x is cosine of x. A dash of pi over 2 then is cosine of pi over 2, which is 0. And if you're in any doubt about this and you want to think about it in terms of the picture, just notice what's going on here at pi over 2. So the value of cosine of pi over 2 is 0. So the graph is just sort of crossing the x-axis at that exact point, pi over 2. So when you're thinking about what the function a is doing in terms of this picture, in terms of the red area that's been accumulated, imagine x varying up and down the line here, up and down the horizontal axis. At the precise instant when x is passing through the point pi over 2, no area is being accumulated, because at that particular instant, there's no area enclosed between the graph of the function and the x-axis. The graph is just, the value there is 0. So I think when you're thinking about this, from the picture itself, we can see why a dash of pi over 2 must be 0, because at that particular instant, as x is passing through this 0 of the function, there's no area being accumulated. Okay, there was a fourth part to that question, which was what is a double dash of pi over 2? So here again, the question is just really asking us to sort of figure out all the notation and to understand exactly what we're being asked for. So we know that a dash of x is cosine of x. That's what the fundamental theorem of calculus tells us about a. It doesn't tell us anything directly about a double dash, but once we know a dash of x, we can find a double dash of x by differentiating that with respect to x. So a double dash of x should be the derivative of cosine x, which is minus sine x. And a double dash of pi over 2 then should be minus sine of pi over 2, which is minus 1. Okay, so I hope that might be of some help. If you're thinking about examples of this type, please do feel free to get in touch with me if you'd like some more examples, or if there's anything about this that's not making sense to you. So thanks very much for watching, and see you later in this week's lectures.